we continue our discussion on the decision tree. So, to recapitulate, we have a training set. If we look at the examples, we have a training set where I have some examples and their corresponding class labels yes or no. So, I want to construct a decision tree of a particular form where each node is an attribute and each branch is a value of the attribute. The leaf nodes correspond to class. So, if an example comes and if we check against the values of the each node, it will follow one of the branch and then we will check another attribute, it will follow another branch till it reaches the leaf. And every leaf is associated with a class, in this case only two, yes and no, and I will classify that example as belonging to that class. So, now the question is, how do we construct the decision tree? That means, which attribute should I check first and then which attribute, where do I stop? All these are part of the decision tree construction. I will explain this with an sort of geometric example. So, as I have told you before, any instance can be described as a vector consisting of the attribute values. So, if for example, we have two attributes, I can represent it by every instance as a two dimensional vector. So, in this figure what I have is I have a set of points in two dimension which are belonging to yes class, I mark them as plus, and no class I mark them as minus. And what I do is that I construct a decision tree of this particular form, where first I check attribute, I check the value of attribute 1, and suppose it is greater than some value, I say it is a leaf belonging to plus class, and then I check if it is greater than some other value and less than this value, it is this region minus class, and if it is less than this certain, so if I call this as V1, V2, if it is greater than V2, so it is if it is greater than V2, I say at this class between V1 and V2, between sorry, the other way around it should be between V1 and V2 this class, and less than V2, less than V1, I have messed up completely. So, less than V1, it is this part. If it is this part, then I again check the value of attribute 2, because whereas this region and this region contains only point from one class, I can infer that belong to that class. Here it is mixed. So, I again check the value of attribute A2, and let us say if it is above a value of u, I check if it is greater than u or less than u. If it is greater than u, I call it as plus. If it is less than u, I call it as minus. So, the point to be noted is that you can visualize any decision tree as a set of axis parallel cuts, which split up the points, training set points into small regions. So, finally, the leaves, they will be one of the region which I do not split further. So, this is a leaf because I do not split it further, this is a leaf, I do not split them, this is a leaf and this is a leaf, I do not split them further. And what I want is the points. Note that again if a new point x, if I push down to the tree, I will just check these cuts and it will be falling in either in this region or this region or this region or this region. A point will fall. I will check the values of attribute and decide. And if these regions are pure, that means contain points from a single class only, I have a good decision tree. Okay. So, I could have as well drawn another decision tree say like this. I could have drawn another decision tree like this. I could have maybe first split on this and then I could have split each of the region further on this and then on this and then on this. Then also I get pure leaf classes. Okay. If you see, it will be a slightly different decision tree. If we actually draw this tree, you will see the previous tree was actually smaller, shallower than this tree. It has less number of checks if conditions. So, I would prefer this tree. So, now I ask you the question that you tell me so this is what I have drawn it. So, this is my tree, this is my decision leaf. Note these values, every decision nodes correspond to a condition, a particular box and a set of samples, training samples which satisfy those conditions and fall in this box. Okay. So, this is my problem. Given a training set, find the best structure. I will follow this top down construction rule for doing this. What I do is start with an empty tree. Okay. Start with an empty tree and then I define something called a best attribute. I will later explain what a best attribute means. So, I choose which attribute is the best, that I choose as my leaf. Say A1 is the best attribute, I choose as my leaf and I make branches for each different value of A1, I make a branch. So, again I will come back to another question that you might have already have is that suppose A1 is continuous valued, A1 has a range of values say temperature or something, then how do I decide the branches? Okay. For the moment I will come back to that question later. For the moment assume that A1 has only a discrete set of values in the domain. Okay. So, now this is a decision attribute. So, if we look at the training examples, say I call it as T, some of the examples will follow this branch, satisfy this condition, some examples will satisfy this condition and some examples will satisfy this condition. Now, as if I recursively carry on this. So, what I do as if I start building a new tree here, but not using these T examples, only these T1 examples, I decide what is the next best node to split. Again what is best I am defining later. Okay. So, I find out an attribute which will split this T1 in the best possible way. To give you a hint, this best possible way corresponds to the way the attribute which sort of discriminates two classes, yes and no classes as much as possible. So, maybe A2 and for here maybe it is A3 and from here maybe it is A4 or something, and then these examples I split further and maybe I get T5, T4 set of examples, T5 set of examples. Note that T4 plus T5 plus T6 will give me T1. Similarly, T1 plus T2 plus T3 will give me all the training examples T. Okay. They are getting distributed among the nodes. Now, if a particular branch all the or if this set of examples T5 belong to a single class, I do not split it further and make this as a leaf, and whatever is the class of T5 I put that class here. Okay. Similarly, I check a node, if it is pure, that means all the points in T6 are from a single class, I make it a leaf, I do not split further. Say they are minus class, I make it like this. Otherwise, I keep on splitting till all the leaf nodes, all the examples belong to a single class. So, till I reach a leaf node, and so I grow the tree and then I stop. Okay. So, if I do it, you can visualize that I will get perfect classification. All the examples, training examples will be perfectly classified. I am not yet commenting on what about future examples, unknown examples. Okay. So, this algorithm is clear, it is a top down algorithm. Initially consider the entire training set, choose an attribute which best splits it. Say it splits into T1, T3 and T2 examples. Each T1 again recursively split further using what is the best example considering T1 only. So, if we actually look at the previous example, it will become clear. It will become clear. So, what I do is that, so initially my entire training set is T. So, initially this entire set is my T. Okay. So, now if I split along A1 into three branches actually, then this is my T1, this is my T2 and this is my T3, they get split. So, I have 3 branches. So, now T1, T2 they are pure, they need not be split further. So, they are, if I call this T1, this as T2, they are leaves. This is a T1 is a plus leaf, T2 is a minus leaf. T3 is not yet pure. So, I have to split it further, but now considering T3, you look A1 attribute 1 is no longer the best attribute to split along. Considering only T3, considering entire T A1 as the split, considering only T3, A2 is a better split, attribute 2 is a better split. Okay. So, I split it further using A2 into say 2 groups. Okay. So, one of the groups become plus and one of the groups become minus plus. So, let me call it as T5 and this as T6. So, this is my T5 and this is my T3 gets split into T5, T6 and then we stop. So, this is the algorithm. So, let me now, sorry. This is the algorithm. So, let me now formally write this down. So, I repeat again, find the best attribute, split on it and on each of the branch again find the best attribute till you get a pure leaf. Now, to answer the next question, what is a best attribute? You think a bit, when we built a tree, we considered the first split, it is better to split along attribute 1. Why? Because this attribute produces as child directly pure classes. Okay. It produces as child the pure classes. So, this purity of class can be sort of used as to decide what is a best attribute. Okay. So, what is a best attribute? So, I can use this. So, okay, let me show it. So, this is the principle what I have already explained. So, this concept of purity of the split, how pure a split leads to, because finally you want a absolutely pure leaf, that is my criteria of best attribute. Okay. So, what is this criteria? The criteria is, if you again look carefully here, is that for example, this one initially this segment was impure, it contained both, and splitting this led to more purity of the child. Okay. So, every split, similarly here this was T3, splitting led to more purity of this and this is still impure. Okay. So, every split should lead to increase in purity, okay, of the resultant boxes. Okay. So, compared to the parent, the childs are purer. How to quantify this? I will quantify this using a function called the entropy. You know, entropy is nothing but a measure of the purity or orderliness or something. So, I will do this. So, let me give an example to do this. Suppose your initial training example, initial training set contain 64 examples, and of them 29 are yes class and 35 are no class. Okay. Suppose using A1, I check a value of A1 is a binary valued attribute which takes on a value true or false. Out of these 64, I see how many examples have A1 equal to true. Let us say 30 examples have A1 equal to true, and remaining 34 examples have A1 equal to false. Out of these 30 examples, 25 are plus, 5 are minus, yes and no, and here 4 are plus, 30 are minus. Whereas, if we split along using attribute A2, this is the picture, and this is the split. So, which split is better? Naturally, this split is better, because here there is a 50-50 mixture of both class. Now, the classes become purer, here still they are mixed. So, naturally, this is a better thing. Okay. So, similarly here, which one is better? Okay. So, what I do is that I define a measure called entropy to do this. The measure is defined this way. Suppose S is my set of training points. So, in the previous case there are 64, S has a size 64. Now, let us say P plus fraction of them are positive yes examples, yes class, and P minus are negative. So, in other words, I can easily define it this way. Suppose you have n examples, of which n plus are positive class, n minus are negative class, then P plus is P plus is n plus by n and P minus is n minus by n. If you have more than 2 classes, you can easily generalize it to fraction belonging to each class. So, it will be, if you have 1, 2, 3 classes, it will be P 1, P 2 and P 3. Okay. So, the entropy of this set of examples S is defined by this formula. It is P plus into minus log of P plus. Note that P plus is a less than 1. So, log of P plus will be negative. So, I put a minus in front. So, P plus into log of P plus P minus into log of P minus. Let us say log base 2, you can actually take any base. So, if you had more class, say 1, 2, 3 class, then I will write P 1 into log of P 1 plus P 2 P 1 into minus log of P 1 plus P 2 into minus log of P 2 plus P 3 into minus log of P 3. Okay. So, suppose this is the S is the entropy. So, now what I can do is the following. I can say for this split, so this is my training set S, I can find its entropy. Let me call it E S. It splits into 2 childs. Let us say I call them set S 1 of these 30 examples and S 2 of these 34 examples. And similarly, I can define entropy for this set S 1 and for this set S 2. I will say the information gain that you get by this split is the reduction in entropy as a result of this split. So, if I define information gain, I can define as entropy of the parent minus sum of entropy of the childs. Okay. So, this is the total entropy of the child E S 1 plus E S 2. E S is the entropy of the parent. The reduction in entropy is the gain in information. Information is kind of negative of entropy. Okay. Now, what I will say is that my best split among these 4 is the one which leads to highest information gain or maximum reduction in entropy. Okay. Or maximum reduction in entropy. So, again if I come back to that illustrative example, so this splits leads to good reduction in entropy because they become purer, whereas this split is, or maybe this kind of split does not lead to much reduction in entropy because the childs are also impure. So, the previous split will be having a better score than this split. Okay. So, look at, if you carefully examine some properties of this entropy, you will notice one thing, that when P plus equal to P minus, there are equal number of points from both class, entropy is the highest. Okay. When there are points from only one class, pure S, only p plus equal to 1, p minus equal to 0, or other way around, p minus equal to 1, p plus equal to 0, then entropy is 0 actually. Okay, entropy is 0. So, the purer the class, that means if we have p plus equal to 1, p minus equal to 0, or p plus equal to 0, p minus equal to 1, pure class, then we have high entropy. Sorry, we have a low entropy, they are pure, less disorderliness. Whereas, if you have p plus equal to p minus equal to 0.5, you have the highest entropy. You can work out the, evaluate the expressions and check. So, my training algorithm is very simple. I just follow this rule, I follow this rule, wait. I follow this rule, I am giving you the description of, yes, description of the algorithm. I follow this rule, recursively split on attributes, first choose the best attribute on the entire training set, then each of the branches individually what is the best attribute, where the best attribute is defined as the amount of information gain that split on that attribute leads to. Okay. And then we stop when there is a 0 entropy or pure leap. So, that is my algorithm. All right. So, I think that is clear. So, that is my algorithm. So, if we I have worked out, I will upload the slide. So, I have worked out all the values, I am not repeating them now. You can check the values that we get. Sometimes there is a slight modification to the entropy value or information gain value. It is I have mentioned entropy of the parent minus sum of the entropy of the child, entropy S1 plus entropy S2. It is sometimes weighted sum of the entropy of the child, where a larger child which has more examples will be given more. So, fraction of examples of S which fall in the child V. So, weighted by that ratio, that is the entropy. Sometimes this form is also used. So, what I will do is that I will use this, if I do, I will do the calculation. So, just to summarize, my algorithm is like that. I will start with the entire training set, see which attributes leads to best information gain, split on that. Now, examples will be distributed across branches, and on each branch again recursively find out which is leads to highest information gain. Do that till each branch contain a 0 entropy or a pure set of examples, pure leaf, then I stop. Okay. So, in the next lecture I will give some more extensions of this on while dealing with not discrete values, but continuous attributes, and on dealing with where training examples contain some noise and overfitting may happen. So, how to deal with that? We will continue that on the next lecture. Thank you for this lecture.